Let's start with something you already know, even if you've never really thought about it this way. Right now, wherever you are, you're being pulled toward the center of the earth. Not in some abstract poetic sense. I mean literally, right now, there is a force acting on every single atom in your body, tugging you downward. You don't think about it. You never think about it. It's just there. And that's kind of the whole story of physics, honestly. It's the story of people who stopped and thought about the things everyone else ignored because they were too obvious, too ordinary, too everywhere to seem interesting. Physics is what happens when someone looks at the world falling down around them and asks, wait, why down? Why not sideways? Why not up? So tonight, we're going to walk through that story, the whole thing, from the very beginning, from the first time a human being looked at the sky and tried to make sense of what was moving up there, all the way through to the strange, almost unsettling ideas that modern physics has handed us. And we're going to take our time with it, because honestly, this story deserves that. It's the story of how we figured out the rules of reality itself, and the people who did it were brilliant, flawed, stubborn, sometimes wrong for decades, and occasionally so far ahead of everyone else that the world didn't catch up for centuries. But let's not start with the famous names. Not yet. Let's start much, much earlier than that. Imagine you're living about 2,500 years ago, somewhere along the coast of what is now Western Turkey. The region is called Ionia, and it's one of the most intellectually alive places on the planet. Trade ships come in from Egypt, from Phoenicia, from all over the Mediterranean, and they bring more than goods. They bring ideas, stories, mathematical techniques, astronomical observations. You're surrounded by people who are asking questions, real questions, about the nature of the world. And the question that matters most, the one that's going to launch everything, is deceptively simple. What is stuff made of? That's it. That's the question. What is the world made of at the most basic level? And a man named Thales of Miletus, gives an answer that sounds almost absurd to us now. He says water. Everything is water. The earth, the air, living things, all of it is some form of water, transformed and rearranged. Now, he's wrong. Obviously, he's wrong. But here's the thing. Being wrong isn't the point. The point is what he's doing. He's saying that the world can be explained by natural principles, not by the whims of gods. He's saying there's an underlying substance, a fundamental thing. And if you can understand that thing, you can understand everything else. That idea, that impulse, is the seed of all of physics. Every particle accelerator, every telescope, every equation scribbled on a whiteboard at 2 a.m. It all traces back to that same instinct. What is stuff made of? What are the rules? Thales had students, and they had students, and pretty soon you've got a whole tradition of thinkers in this part of the Greek world who are all wrestling with this question. Anaximander, who studied under Thales, said no, it's not water. It's something more fundamental, something he called the apeiron, the boundless, this infinite, undefined substance that gives rise to everything. Anaximenes said it was air, and that everything else was just air, compressed or rarefied to different degrees. Heraclitus, over in Ephesus, said fire, and argued that change itself was the fundamental nature of reality. Everything flows. Nothing stays the same. You might know his famous line, even if you don't know it's his. You can't step into the same river twice. And then, around 450 BCE or so, you get two thinkers, Leucippus and his student Democritus, who come up with an idea so far ahead of its time that it's almost eerie. They say the world is made of atoms, tiny, indivisible particles. The word atomos literally means uncuttable, moving through empty space, colliding, combining, separating. Everything you see, everything you touch, is just atoms and void. That's it. There's no mystical substance, no divine fire, just tiny pieces of matter bouncing around in emptiness. Think about what that means. 2,400 years before we had electron microscopes, before we had particle physics, before we had any of the tools that let us actually see the atomic world, these two guys sat down and reasoned their way to the idea that matter is granular, that if you kept cutting something in half, eventually you'd reach a point where you couldn't cut anymore. They didn't have proof. They couldn't have had proof. They just thought really, really carefully about the nature of change and substance and came up with an answer that turned out to be, in its broad strokes, remarkably close to right. Now here's where the story takes a turn that shaped the next 2,000 years of physics, and not entirely for the better. Because the most influential thinker in the ancient world wasn't Democritus. It was Aristotle. Aristotle was born in 384 BCE in Stagira, a small town in northern Greece. His father was the personal physician to the king of Macedon, which meant Aristotle grew up around the court, around power, around people who valued knowledge as a practical tool. When he was 17, he went to Athens to study at Plato's academy, and he stayed there for 20 years. 20 years. That's not a casual education. He absorbed everything Plato had to teach, and then he went further, much further, into territory Plato never explored: biology, zoology, meteorology, physics, logic, ethics, politics. The scope of what this one person tried to understand is honestly staggering. And when it came to physics, to understanding motion and matter and the structure of the cosmos, Aristotle built a system, a complete, coherent, internally consistent system that explained, or seemed to explain, pretty much everything people could observe. Here's how it worked. Aristotle said there were 4 elements: earth, water, air, and fire. Each had a natural place. Earth belonged at the center of the cosmos, which is why heavy things fall. They're seeking their natural place. Water sits above earth, air above water, fire above air. Everything in the terrestrial realm was made of some combination of these 4. And motion happened because things were trying to get where they belonged. A rock falls because it's mostly earth, and earth belongs at the bottom. Smoke rises because it's mostly air and fire, and those belong up high. It's elegant, actually. It has a certain intuitive beauty to it. But here's the thing. Aristotle also said something about motion that would cause problems for a very long time. He said that for something to keep moving, something has to keep pushing it. If you stop pushing, the object stops. This seems reasonable, right? Push a box across the floor, and when you stop pushing, it stops. But it's wrong. It's deeply wrong, and it took almost 2,000 years for someone to clearly articulate why. The problem is friction. Aristotle was watching objects move through a world full of friction, air resistance, rough surfaces, all of it, and he was generalizing from that experience. He never imagined what would happen if you could remove all that resistance. If you could put a ball on a perfectly smooth, perfectly flat surface in a vacuum and give it a push, it would just keep going, forever. No force needed. That's inertia, and it's one of the most fundamental ideas in all of physics. But Aristotle missed it because the world he could observe was a world where friction was everywhere, invisible and unaccounted for. He also divided the cosmos into two completely separate realms. Down here, in the sublunary world, everything below the moon, things were messy, changeable, made of those four elements, subject to decay and transformation. But up there, in the celestial realm, everything was perfect. The stars and planets were made of a fifth element, the quintessence, and they moved in perfect circles because circles were the most perfect shape. The heavens were eternal, unchanging, fundamentally different from the grubby, imperfect world below. This division, terrestrial physics over here, celestial physics over there, and never the two shall meet, was one of the biggest conceptual barriers in the history of science, because it meant that for centuries, nobody thought to apply the same rules to falling apples and orbiting planets. Those were different categories of thing, governed by different principles. It would take a very specific kind of genius to look at the moon and a cannonball and say, you know what? The same force is acting on both of those. But we're getting ahead of ourselves. That genius won't be born for almost 2,000 years. What's remarkable about Aristotle's system is how long it lasted. And it lasted not because people were stupid or lazy. It lasted because it worked, in a practical, everyday sense. It explained what people could see. Heavy things fall faster than light things, right? Well, actually, no, they don't. Not in a vacuum. But in air, a rock does fall faster than a feather. And if you don't know about air resistance, Aristotle's explanation seems perfectly adequate. His physics was wrong, but it was wrong in ways that were very hard to detect without careful experimentation, and careful experimentation wasn't really the style of ancient Greek philosophy. They were thinkers, reasoners, arguers. The idea that you should go out and actually drop things off towers and time them, that was a different kind of intellectual culture, and it hadn't arrived yet. So Aristotle's physics became the physics. His works were studied, copied, commented on, and taught across the Greek world, then the Roman world, then, and this is a crucial part of the story, the Islamic world. When the Western Roman Empire collapsed and much of Europe entered a period of relative intellectual dormancy, it was scholars in Baghdad, in Cordoba, in Cairo, who preserved and extended Greek knowledge. The House of Wisdom in Baghdad, founded in the early 9th century under the Abbasid caliphs, became one of the great intellectual centers of human history. Scholars there translated Aristotle, Euclid, Ptolemy, Galen, the entire corpus of Greek learning, into Arabic, and they didn't just translate. They critiqued, they extended, they pushed further, and some of them started pushing back against Aristotle's physics in really interesting ways. A scholar named Ibn al-Haytham, working in Cairo around the year 1000, did something genuinely revolutionary with optics, the study of light and vision. Before him, there was a widespread belief, going back to Euclid and Ptolemy, that vision worked by rays shooting out of your eyes and touching objects. Ibn al-Haytham said no. Light comes from sources like the sun, bounces off objects, and enters your eye. That's how you see. And he didn't just assert this, he tested it. He built a camera obscura, a dark room with a tiny hole in one wall, and showed that light from outside projected an inverted image on the opposite wall. He experimented with lenses, with mirrors, with refraction. He wrote a 7-volume treatise called The Book of Optics that became one of the most influential scientific works ever written. Some historians call him the first true physicist because he combined mathematical rigor with systematic experimentation in a way that nobody before him had quite managed. And then there was a thinker named Ibn Sina. You might know him as Avicenna, who, among his many contributions, started questioning Aristotle's ideas about motion. He proposed something he called male, an acquired force that a projectile carries with it after being thrown. This was a step toward the concept of momentum, toward the idea that motion doesn't need a continuous push. It's not the full picture, not yet, but it's a crack in the Aristotelian wall, a crack that would widen over the centuries. Meanwhile, in medieval Europe, Aristotle's works were being rediscovered, largely through Arabic translations, and they hit the universities like a thunderbolt. The University of Paris, Oxford, Bologna. These new institutions of learning were hungry for systematic knowledge, and Aristotle provided a complete framework. Thomas Aquinas spent much of his career reconciling Aristotelian philosophy with Christian theology, creating a grand synthesis that made Aristotle's physics almost a matter of religious orthodoxy. Questioning Aristotle wasn't just intellectually bold, it could be seen as questioning the entire structure of knowledge that the Church had embraced. But people questioned anyway. At the University of Paris in the 14th century, a scholar named Jean Buridan developed his theory of impetus. Essentially the same idea as Ibn Sina's male, arrived at somewhat independently. When you throw a ball, Buridan said, you impart to it an impetus, an internal motive force, and that impetus is what keeps it moving after it leaves your hand. The ball slows down because air resistance and gravity gradually drain the impetus away. This is still not quite right. The modern concept of inertia says the ball doesn't need any internal force to keep moving, it just needs nothing to stop it. But Buridan's impetus theory was a huge step forward. It was the beginning of the end for Aristotelian physics, even though nobody knew it yet. And Buridan did something else that was quietly radical. He applied his impetus theory to the heavens. He suggested that God might have given the celestial spheres an initial impetus at the moment of creation, and that they'd been spinning ever since, no angels required to push them along. That's a subtle but profound shift. It's starting to erase Aristotle's hard line between terrestrial and celestial physics. It's saying maybe the same principles work up there as down here. Maybe the universe isn't divided into two separate kingdoms with two separate sets of rules. Buridan's student, Nicole Oresme, went even further. Oresme was a bishop, a mathematician, and one of the most original thinkers of the medieval period. He developed a way of graphing velocity against time, essentially inventing a primitive version of what we'd now call kinematics, the mathematical description of motion. He proved the mean speed theorem, which says that a uniformly accelerating body covers the same distance as a body moving at constant speed, equal to the average of the initial and final velocities. That sounds technical, but think about what it means. He's taking motion, something that seems fluid and continuous and hard to pin down, and he's turning it into geometry. He's making it mathematical. And he's doing this in the 1350s, almost 300 years before Galileo. Speaking of Galileo, and this is where the story really starts to accelerate, if you'll pardon the pun. There's a common myth that Galileo invented physics out of nothing, that he was this lone genius who single-handedly overthrew Aristotle and started modern science from scratch. The truth is more interesting than that. Galileo stood on the shoulders of a long line of thinkers, Buridan, Oresme, Ibn al-Haytham, Ibn Sina, and many others, who had been slowly, carefully, sometimes dangerously chipping away at the Aristotelian edifice for centuries. What Galileo did was bring together mathematical rigor, systematic experimentation, and a kind of fearless intellectual combativeness that forced the world to pay attention. He was born in Pisa in 1564, And from the very beginning, he was the kind of person who couldn't leave a bad idea unchallenged. His father was a musician and music theorist who had conducted experiments on the relationship between string tension and pitch. So Galileo grew up in a household where testing ideas against reality was just what you did. That matters. That background matters. Because when Galileo later insisted that you had to actually measure things, actually time things, actually watch what nature does instead of just reasoning about what it should do, he wasn't inventing that attitude from nothing. He'd absorbed it at the dinner table. And one of the first things he turned that attitude toward was falling bodies. Aristotle had said that heavier objects fall faster. A 10-pound weight should fall 10 times faster than a 1-pound weight. And for almost 2,000 years, people had just accepted that. But Galileo, probably in the late 1580s, started actually testing it. Now, the famous story about dropping balls from the Leaning Tower of Pisa is probably more legend than fact. His student Viviani told that story decades later, and there's no contemporary evidence it happened quite that way. But Galileo definitely did experiments with falling objects, and more importantly, with inclined planes, which let him slow down the motion of falling so he could actually measure it with the crude timekeeping available to him. And what he found was extraordinary. He found that all objects, regardless of weight, accelerate at the same rate when you account for air resistance. A cannonball and a musket ball, dropped from the same height in a vacuum, would hit the ground at exactly the same moment. And the distance they covered increased with the square of the time, double the time, quadruple the distance. That relationship, that beautiful mathematical regularity hiding inside something as ordinary as a falling rock, was a revelation. It was the first time anyone had taken a piece of everyday experience, something falling, and shown that underneath the mess and the noise, there was a clean, precise, mathematical law governing what happened. Not a tendency, not a rough guideline, but an exact relationship you could write down and use to predict the future. If I tell you how long something has been falling, you can tell me exactly how far it's gone. That idea, that nature speaks mathematics, that the book of the universe is written in geometric figures and numbers. Galileo said almost exactly that, and he meant it. He really believed, and he was right, that the physical world follows rules you can express as equations, and that finding those equations is what it means to understand nature. But here's where things get even more interesting. Because once Galileo started thinking carefully about motion, he stumbled into something that would eventually become one of the most important ideas in all of physics. He noticed that if you roll a ball along a perfectly smooth, perfectly level surface, no friction, no resistance, there's no reason for it to stop. It wouldn't speed up, it wouldn't slow down, it would just keep going, forever. Now, that sounds obvious to us, but think about what it means in the context of everything that came before. Aristotle had said that everything that moves needs something to keep pushing it. Remove the push, and the motion stops. That was the common sense view, and honestly, it matches what you see in daily life. You stop pushing a box across the floor, and it stops moving. Buridan's impetus theory had gotten partway to questioning that, suggesting that the push gets embedded in the object somehow. But Galileo went further. He said no, the natural state of a moving object isn't to stop. The natural state is to keep moving. It's only friction and air resistance and other forces that slow things down. If you could remove all of those, motion would continue indefinitely. This is essentially the principle of inertia, and it was a complete inversion of Aristotelian thinking. Aristotle had said, rest is the natural state, and motion requires explanation. Galileo was saying, motion is just as natural as rest, and what requires explanation is any change in motion, speeding up, slowing down, changing direction. That shift, that quiet conceptual revolution, is one of the most profound things that ever happened in physics. And Galileo didn't state it in its final, polished form. That would come later. But he saw it. He grasped the essential truth of it, and it changed everything that followed. Now, around the same time Galileo was figuring all this out, he was also turning his attention to the sky. In 1609, he heard about a new invention from the Netherlands, a device that used lenses to make distant objects appear closer. A spyglass, basically. Galileo didn't invent the telescope, but he did something arguably more important. He pointed it upward. Within months, he had built his own improved version, with maybe 8 or 9 times magnification at first, eventually getting up to about 20 or 30 times. And when he looked at the moon, he didn't see the perfect, smooth, crystalline sphere that Aristotle's cosmology demanded. He saw mountains. He saw craters. He saw shadows that shifted as the angle of sunlight changed, exactly the way shadows behave on rough terrain here on Earth. The moon, it turned out, was a place, a world with geography, not some fundamentally different kind of substance floating in an ethereal realm. And that was just the beginning. He looked at Jupiter and discovered 4 moons orbiting it. The Galilean moons, we call them now, Io, Europa, Ganymede, and Callisto. Think about what that meant. Here were objects clearly orbiting something other than the Earth. The whole Aristotelian and Ptolemaic system was built on the assumption that everything revolves around the Earth. And here was a miniature solar system, right there in his telescope, proving that celestial bodies could orbit other celestial bodies. He observed the phases of Venus, which showed that Venus orbits the Sun, not the Earth. He saw that the Milky Way, that hazy band across the sky, was actually made up of countless individual stars too faint to see with the naked eye. He published these observations in 1610 in a little book called Sidereus Nuncius, the Starry Messenger, and it caused a sensation. Almost overnight, Galileo became the most famous scientist in Europe, but it also set him on a collision course with the Catholic Church, because all of these observations pointed toward the same conclusion. Copernicus had been right. The Earth goes around the Sun, not the other way around. Copernicus had proposed this back in 1543, but his model had been treated mostly as a mathematical convenience, a useful trick for calculating planetary positions without necessarily being literally true. Galileo was saying, no, this is actually how things are. The Earth really moves. And here's where the story gets painful. Because Galileo was right, and he knew he was right, and he wasn't particularly diplomatic about it. He had a sharp tongue and a gift for making people who disagreed with him feel foolish. In 1632, he published his dialogue concerning the 2 chief world systems, which was structured as a conversation between 3 characters, one arguing for the Copernican system, one for the Ptolemaic, and one supposedly neutral. But the character defending the Ptolemaic system was named Simplicio, which sounds an awful lot like simpleton in Italian, and Galileo put some of the Pope's own arguments into Simplicio's mouth. Urban VIII, who had actually been somewhat friendly to Galileo before this, was furious. The Inquisition put Galileo on trial in 1633, and he was found vehemently suspect of heresy, forced to recant, and spent the rest of his life under house arrest. The famous story that he muttered, "And yet it moves," et pour s'y mouve, after his recantation is almost certainly a later invention, but it captures something true about the situation. The earth does move. No amount of institutional authority could change that. What's remarkable is that even under house arrest, Galileo kept working. In 1638, he published his Discourses and Mathematical Demonstrations relating to two new sciences, which laid out his work on mechanics and the strength of materials. This is really where his physics lives, the kinematics, the parabolic trajectories of projectiles, the analysis of beams and structures. He was old and going blind by then, and the book had to be smuggled out of Italy to be published in the Netherlands. But it got out, and it changed everything. So let's take a breath here and think about what Galileo actually accomplished. He established that the laws of physics can be discovered through careful experiment and expressed mathematically. He showed that all objects fall at the same rate, regardless of weight. He discovered the principle of inertia, that motion doesn't require a continuous force. He provided overwhelming observational evidence for the heliocentric model, and he did all of this while fighting against the most powerful institution in Europe. Not bad for one lifetime. But Galileo left a lot of loose ends. He had the principle of inertia in rough form, but he hadn't stated it precisely. He understood acceleration, but he didn't have a complete theory of force. He knew that projectiles follow parabolic paths, but he couldn't explain why planets follow elliptical ones. For that, you need someone who could take all these scattered insights and weave them into a single, unified framework, and that someone was born on Christmas Day, 1642, the same year Galileo died. His name was Isaac Newton, and honestly, what he accomplished is so staggering that it's hard to know where to begin. But let's try. Newton grew up in Woolsthorpe, a small village in Lincolnshire, England. His father died before he was born. His mother remarried when he was 3 and left him with his grandmother, and by all accounts, he was a lonely, intense, somewhat difficult child. He was not warm. He was not charming. He held grudges for decades and could be genuinely cruel to people who crossed him. But he had a mind unlike anything the world had seen before, or, some would argue, has seen since. He went to Cambridge in 1661, and at first he was an unremarkable student. But he was reading voraciously: Descartes, Kepler, Galileo, the latest mathematics, and teaching himself things far beyond the curriculum. Then in 1665, the plague hit England. Cambridge closed. Newton went home to Woolsthorpe, and over the next 18 months or so, in the quiet of the English countryside, he essentially reinvented the intellectual world. He developed calculus, the mathematics of change, of things that vary continuously. He conducted experiments with prisms showing that white light is actually a mixture of all colors. And he began thinking about gravity. The apple story, you know the one, is actually somewhat grounded in reality. Newton himself told the story late in life, saying that seeing an apple fall in the garden at Woolsthorpe got him thinking about whether the same force that pulls the apple down might extend much further than anyone imagined. What if it reaches all the way to the moon? What if the moon is, in a sense, falling toward the earth, just like that apple, but moving sideways fast enough that it keeps missing? That's a wild thought. Picture it. The moon is falling, constantly falling, but the earth curves away beneath it at exactly the right rate, so it falls forever in a circle. Well, an ellipse technically. And the force that makes the apple drop and the force that keeps the moon in orbit are the same force, following the same law. That idea, that single unifying leap is what separates Newton from everyone who came before, because people had thought about gravity before him. They knew things fell. They knew the planets moved. But nobody had dared to say it was all one thing, one force, one law, operating the same way here on the ground as it does out there among the celestial bodies. Remember that old Aristotelian divide, the idea that the heavens and the earth play by different rules, that the stuff up there is fundamentally different from the stuff down here? Newton demolished it. Not with philosophy, not with argument, but with mathematics. He showed that you could take one equation and use it to predict both the trajectory of a cannonball and the orbit of Jupiter. Same equation, same force, same universe. And here's the thing about how he figured out the shape of that law. He knew from Kepler's work, those 3 laws of planetary motion we touched on, that the planets sweep out equal areas in equal times and that their orbital periods relate to their distances in a very specific mathematical way. Newton asked himself, what kind of force would produce exactly that behavior? And the answer, when he worked through the geometry, was a force that decreases with the square of the distance. Double the distance, the force drops to 1/4. Triple it, the force drops to 1/9. That's the inverse square law, and it's one of the most important relationships in all of physics. It shows up everywhere. Gravity, light intensity, electric fields. There's something almost geometrically inevitable about it, because it has to do with how things spread out over the surface of a sphere, and the surface area of a sphere grows with the square of the radius. So if a force radiates outward in all directions equally, it naturally dilutes by that square factor. Newton saw this, but he didn't publish it. Not right away. Not for years, actually. This is one of the maddening things about Newton. He would make these extraordinary discoveries and then just sit on them. He'd write them up in notebooks, maybe share a few hints with colleagues, and then move on to something else. The calculus, the optics, the gravity work, all of it stayed mostly private through the late 1660s and into the 1670s. Part of it was his personality. He hated criticism. He hated public disputes. He'd had a bruising experience when he published some of his optical findings, and Robert Hooke, a brilliant but combative scientist at the Royal Society, had attacked his conclusions. Newton was so upset by the exchange that he basically withdrew from scientific correspondence for years. He later said he'd learned that philosophy, meaning natural philosophy, what we'd call science, was such an impertinently litigious lady that a man had as good be engaged in lawsuits as have to do with her. That's Newton telling you he'd rather deal with lawyers than argue about science. That's how badly the criticism stung. So the gravity work sat. And it might have sat indefinitely, if not for a conversation in a London coffee house in January 1684. 3 men were talking: Robert Hooke, Edmund Halley, yes, the comet guy, and Christopher Wren, who was not just an architect, but a serious mathematician. They were discussing the problem of planetary motion. Hooke claimed he had a proof that an inverse square force would produce elliptical orbits, but he never produced it. Wren offered a prize, a book worth 40 shillings, to whoever could deliver the proof within 2 months. Nobody did. So that August, Halley traveled to Cambridge and went to see Newton directly. He asked him, if a force decreased with the square of the distance, what shape would the orbit be? And Newton answered immediately, an ellipse. Halley was stunned. He asked how Newton knew. Newton said he'd calculated it years ago. Halley asked to see the proof, and Newton rummaged around but couldn't find it right then. He promised to redo it and send it along. What Newton sent was a short manuscript called De Motu, On Motion, and it was extraordinary. But more importantly, it got Newton going again. The act of writing up that proof pulled him back into the problem, and once Newton was pulled into a problem, he didn't come out until he'd exhausted it. Over the next 18 months, he worked with an intensity that's almost frightening to read about. He barely ate, he barely slept. His secretary later recalled that Newton would sometimes forget whether he'd had dinner, or he'd get up in the morning, sit on the edge of his bed with a thought, and still be sitting there hours later, half-dressed, lost in calculation. What emerged from this period of furious work was the Principia, the Philosophiae Naturalis, Principia Mathematica, the mathematical principles of natural philosophy, published in 1687, largely thanks to Halley, who not only encouraged Newton, but actually paid for the printing out of his own pocket. And the Principia is... Look, it's hard to overstate what this book is. It might be the single most important scientific work ever written. In it, Newton lays out 3 laws of motion and the law of universal gravitation, and then he uses them to explain an astonishing range of phenomena. Let's walk through those laws, because they're the foundation of everything that comes after, and they're beautiful in their simplicity. The first law says that an object at rest stays at rest, and an object in motion stays in motion in a straight line at constant speed, unless a force acts on it. That's inertia, and you can hear Galileo's fingerprints all over it. But Newton states it with a clarity and generality that Galileo never quite achieved. It tells you that motion doesn't need a cause. Stillness and steady motion are the same thing, physically speaking. Only changes in motion need explaining. The second law tells you exactly how force relates to that change. Force equals mass times acceleration. Push something twice as hard, it accelerates twice as fast. Try to push something twice as heavy, it accelerates half as fast. This is the workhorse equation of all classical mechanics. Every engineering calculation about loads and stresses and trajectories, every bridge and building and airplane, ultimately traces back to this relationship. It gives you a precise quantitative tool for predicting how things move. The third law says that for every action, there's an equal and opposite reaction. You push on a wall, the wall pushes back on you just as hard. A rocket expels gas downward, and the gas pushes the rocket upward. This one sounds simple, and it is, but its implications are profound. It means forces always come in pairs. You can never have a force acting in isolation. The Earth pulls on the moon, and the moon pulls on the Earth. You're pulling on the planet right now, just as it's pulling on you. Your pull is just too tiny to notice. And then there's the law of gravitation itself. Every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. That's it. That's the whole law. And from these 3 laws of motion and this one law of gravity, Newton derives the orbits of the planets, the shape of the Earth, the behavior of comets, the cause of tides, the precession of the equinoxes, the motion of the moon with all its complicated wobbles. He explains why Jupiter is slightly flattened at the poles. He calculates the speed of sound in air. The scope is breathtaking. Now, the Principia wasn't easy to read. Newton deliberately made it difficult, partly because he wrote it in the geometric style of the ancients, rather than using his own calculus. Some historians think he did this to make it more rigorous. Others think he did it to make it harder for lesser minds to criticize. Either way, it was a monument. When the French mathematician the Marquis de l'Hôpital first encountered Newton's work, he reportedly asked, "Does he eat, drink, and sleep like other men? I cannot believe otherwise than that he is a god." But here's the thing about Newton's triumph. It created a new kind of problem. His law of gravitation described how gravity behaved with extraordinary precision. It told you exactly how the force depended on mass and distance, but it didn't tell you why. It didn't explain what gravity is, or how the sun reaches across 93 million miles of empty space to pull on the Earth. Newton himself was uncomfortable with this. He called it action at a distance, and he admitted it was philosophically troubling. In a famous letter, he wrote that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He's saying, I know this is weird. I know it doesn't make sense that objects pull on each other across empty space with nothing in between. But the math works, and I'm not going to pretend I have an explanation I don't have. He famously wrote, "Hypotheses non fingo. I frame no hypotheses. I'm telling you what happens, not why." And that question, the why of gravity, would remain unanswered for over 200 years, until a quiet patent clerk in Switzerland started thinking about elevators and falling painters. But we'll get there. For now, what matters is what Newton's framework made possible. Because once you have precise mathematical laws governing motion and force, you can start engineering the world in a fundamentally new way. You can predict things. You can calculate trajectories before you fire the cannon. You can figure out how strong a beam needs to be before you build the bridge. You can move from trial and error to design. And that's exactly what happened in the century after the Principia. Newtonian mechanics became the operating system of the physical sciences. People like Leonhard Euler, the great Swiss mathematician who was so prolific it's almost comical. He published over 800 papers. He kept working even after going blind, dictating to his sons. Euler took Newton's framework and extended it into fluid dynamics, rigid body rotation, the calculus of variations. Joseph Louis Lagrange reformulated Newtonian mechanics into a more elegant mathematical framework that made certain problems much easier to solve. Pierre-Simon Laplace applied Newton's gravitational theory to the solar system with such thoroughness that he could account for tiny perturbations in planetary orbits that Newton himself hadn't been able to explain. When Napoleon reportedly asked Laplace where God fit into his system of celestial mechanics, Laplace is said to have replied, "I had no need of that hypothesis." But alongside this magnificent mechanical worldview, something else was happening. People were starting to think seriously about a phenomenon that Newton's laws didn't obviously address, something you encounter every single day, but that turned out to be far stranger and more fundamental than anyone in the 17th century could have guessed. Heat. What is heat, really? Is it a substance? A fluid? A kind of motion? By the middle of the 18th century, the dominant theory was that heat was a weightless, invisible fluid called caloric that flowed from hot objects to cold ones, like water flowing downhill. It was a tidy idea. It explained a lot of everyday observations. But there were cracks in it, and those cracks were about to be blown wide open by a man who spent his days boring cannons for the Bavarian army, a man named Benjamin Thompson, who would later become Count Rumford. And what a character he was. Born in 1753 in a small town in Massachusetts, Woburn, actually, Thompson was one of those restless, ambitious, endlessly curious people who seemed to show up at every turning point in history. He married a wealthy widow when he was barely 20, got involved in colonial politics on the Loyalist side during the American Revolution, which meant he had to flee to England when the war went badly for the British. From there, he ended up in Bavaria, working for the Elector, reorganizing the army, redesigning military equipment, and somehow along the way getting himself made a count of the Holy Roman Empire. He chose the title Rumford, after the old name for Concord, New Hampshire, where he'd once lived. So here's this American-born, British-allied, Bavarian-employed aristocrat, and he's supervising the boring of brass cannons in Munich around 1798, and he notices something that bugs him. The caloric theory said that when you drilled into metal, you were releasing the caloric fluid trapped inside it. That's why the metal got hot. You were squeezing the caloric out, the way you might squeeze water out of a sponge. Fine. But Rumford noticed that the heat just kept coming. As long as the boring tool kept grinding against the brass, heat kept pouring out. He famously demonstrated that you could boil water with the heat generated by a blunt boring tool. A tool so dull it was barely cutting any metal at all. If heat were a substance stored in the metal, it should eventually run out. You'd squeeze all the caloric out, and the metal would stop getting hot. But it didn't stop. It just kept going, as long as there was mechanical work being done. Rumford concluded that heat couldn't be a material substance. It had to be something related to motion, the motion of the particles making up the metal. And he was right, though it would take another half-century for that idea to be fully worked out. At the time, plenty of people weren't convinced. The caloric theory was too useful, too well established, too comfortable. It explained conduction. It explained why ice melts. Caloric flows in and loosens the rigid structure. It had a mathematical framework that worked for engineering calculations. So Rumford's cannon boring experiments were noted, discussed, and then sort of filed away as an interesting anomaly, which is a pattern you see again and again in physics. Someone makes a crucial observation, and the field isn't ready to absorb it yet. But the question of heat wouldn't go away, because the Industrial Revolution was making it impossible to ignore. By the early 19th century, steam engines were everywhere, powering factories, pumping water out of mines, driving locomotives. And the people building and improving these engines desperately needed to understand the relationship between heat and mechanical work. This wasn't abstract philosophy anymore. This was money. This was empire. If you could make a steam engine even a few % more efficient, you could save enormous amounts of coal, and coal cost real money. Enter a young French military engineer named Sadi Carnot. And here's the thing about Carnot. He published exactly one significant work in his entire life, a slim little book in 1824 called Reflections on the Motive Power of Fire. He was only 28 years old, and in that book, working within the caloric framework that he'd inherited, he still thought heat was a fluid. He managed to derive one of the most profound results in all of physics. Carnot asked a deceptively simple question. What is the maximum possible efficiency of a heat engine? Not any particular engine, not a Watt engine or a Newcomen engine, but any engine that converts heat into work. Is there a theoretical ceiling? And he found that yes, there is. The maximum efficiency depends only on the temperatures between which the engine operates, the temperature of the hot source and the temperature of the cold sink. That's it. It doesn't matter what the engine is made of, what fuel it burns, how cleverly it's designed. There's a hard limit set by those two temperatures. The bigger the temperature difference, the more efficient the engine can theoretically be. But you can never reach 100%. You can never convert all the heat into useful work. Some heat always has to be dumped into the cold reservoir. Think about what that means. Carnot was saying there's a fundamental constraint built into the universe itself, not a limitation of our engineering skill, but a law of nature. No matter how clever you are, no matter how perfect your machine, you cannot beat this limit. And he derived it from pure reasoning about idealized cycles, what we now call Carnot cycles. It's breathtaking, really. A 28-year-old French engineer working with an incorrect theory of what heat actually is, nonetheless arrived at a result that is absolutely correct and still foundational to every branch of physics and engineering today. Tragically, Carnot died of cholera in 1832, at just 36. His work was largely ignored for over a decade. His notes, discovered after his death, show that he was actually moving toward the correct understanding of heat as a form of energy rather than a substance. He was abandoning caloric on his own. But those notes weren't published for years. The world almost lost his contribution entirely. It took others to pick up the thread. In the 1840s and 1850s, several people converged independently on the idea that would become the first law of thermodynamics, the conservation of energy. James Prescott Joule, a brewer's son from Manchester, England, performed meticulous experiments showing that mechanical work could be converted into a precise, measurable amount of heat. His most famous apparatus used falling weights to spin paddle wheels inside an insulated container of water, and he measured the tiny temperature increase with extraordinary precision. Joule showed that a specific amount of mechanical work always produced the same amount of heat. Always. It was a conversion, not a creation. Energy was being transformed from one form to another, but the total amount was conserved. Meanwhile, a German physician named Julius Robert von Mayer had actually published essentially the same idea a few years earlier, in 1842, based on observations he'd made as a ship's doctor in the tropics. He noticed that venous blood was redder in hot climates, which led him to think about the relationship between body heat, food energy, and mechanical work. But Mayer's paper was poorly received, partly because he wasn't a physicist by training, and his arguments were more philosophical than experimental. He suffered terribly for it. He had a breakdown, attempted suicide, was committed to an asylum. The priority dispute between Mayer and Joule became one of those painful episodes in the history of science where the question of who got there first caused real human suffering. But by the 1850s, the pieces were falling into place. The first law of thermodynamics, energy is conserved, it can change forms but never be created or destroyed, was becoming established. And then came the second law, which is arguably even more profound and certainly stranger. This is where a German physicist named Rudolf Clausius and a Scottish-Irish physicist named William Thomson, later Lord Kelvin, made their great contributions. Clausius, building on Carnot's work, articulated what the second law really means. He introduced a concept he called entropy, from the Greek word for transformation. And entropy is one of those ideas that sounds simple at first, but gets deeper and more unsettling the longer you think about it. Here's the basic statement. In any natural process, the total entropy of a closed system either stays the same or increases. It never decreases. Heat flows from hot to cold, never from cold to hot, spontaneously. A broken egg doesn't unbreak. A cup of coffee left on your desk cools down to room temperature. It never spontaneously heats up by absorbing energy from the cooler air around it. These aren't just practical observations. They're expressions of a deep asymmetry built into the fabric of reality. Now, you might be thinking, wait, doesn't a refrigerator move heat from cold to hot? Yes, it does. But it requires work to do so. You have to plug it in. You have to spend energy. And when you account for all the energy flows, the electrical energy consumed, the heat dumped out the back of the fridge into your kitchen, the total entropy of the whole system has increased. The second law isn't violated. It's satisfied, with room to spare. Clausius summed up both laws of thermodynamics in a pair of sentences that are as elegant as anything in physics. The energy of the universe is constant. The entropy of the universe tends toward a maximum. That second statement has enormous implications. It means the universe is running down. It means there's a directionality to time. Things move from order to disorder, from useful energy to waste heat, from structure to randomness. The second law gives time its arrow. And that's something Newton's laws never did. Newton's equations work perfectly well running forward or backward in time. If you filmed a billiard ball bouncing around a table and played the film in reverse, it would look perfectly plausible. Newton's laws can't tell you which direction is forward, but the second law can. Entropy increases. That's how you know which way time flows. And here's what's really beautiful. In the 1870s, an Austrian physicist named Ludwig Boltzmann figured out why. Boltzmann connected thermodynamics to the microscopic world of atoms and molecules, and he showed that entropy is fundamentally a statistical concept. It's about probability. A state of high entropy isn't somehow preferred by the universe because of some mysterious force. It's just overwhelmingly more likely. There are vastly more ways for molecules to be disordered than ordered, just as there are vastly more ways to shuffle a deck of cards into a random arrangement than into perfect suit and rank order. The universe doesn't tend toward disorder because it wants to. It tends toward disorder because disorder is astronomically more probable. Boltzmann captured this insight in his famous equation, S equals K log W. Entropy equals Boltzmann's constant times the logarithm of the number of microstates. It's carved on his tombstone in Vienna. And the story behind that equation, and behind Boltzmann himself, is one of the most poignant in all of physics. Because Boltzmann spent decades defending the atomic hypothesis, the idea that matter really is made of atoms, against fierce opposition from some of the most prominent physicists and philosophers of his era. People like Ernst Mach and Wilhelm Ostwald argued that atoms were just convenient fictions, mathematical tricks with no physical reality. They attacked Boltzmann relentlessly, and Boltzmann, who was prone to depression and self-doubt, took it hard. In 1906, while on vacation with his family near Trieste, he hanged himself. He was 62. Just a few years later, Einstein's work on Brownian motion and Jean Perrin's experiments would definitively confirm the existence of atoms, vindicating everything Boltzmann had fought for. He never got to see it. But let's step back for a moment. Because while thermodynamics was reshaping how people understood energy and entropy and the direction of time, something else entirely was happening in physics, something that would prove just as revolutionary, maybe more so. And it started with a simple question that people had been asking since antiquity, a question that seems almost childlike in its simplicity. What is light? Is it a stream of particles? Is it a wave? And if it's a wave, what is it waving through? By the early 19th century, this question was about to get a spectacular answer, and the person who cracked it open was a man who had taught himself to read by the age of 2, and who could speak over a dozen languages before he reached adulthood. Thomas Young. And Young is one of those figures in the history of science who makes you feel a little inadequate, honestly, because the man was good at everything. He was a physician, a linguist. He helped decipher the Rosetta Stone, by the way. A physiologist who figured out how the eye focuses on objects at different distances, and, almost casually, the person who demonstrated that light behaves as a wave in one of the most elegant experiments ever devised. Now, to understand why Young's work mattered so much, you have to appreciate the state of the debate he was walking into. Newton, the giant whose shadow still loomed over all of physics a century after his death, had argued that light was made of tiny particles, which he called corpuscles. And Newton's authority was so immense, especially in Britain, that questioning his particle theory of light felt almost like heresy. There were good reasons to take the corpuscle idea seriously, too. Light travels in straight lines. It bounces off mirrors the way a ball bounces off a wall. It casts sharp shadows. All of that feels very particle-like if you think about it. But there had always been another camp. Christian Huygens, the Dutch physicist, had proposed back in 1678 that light was a wave, and he'd shown that you could explain reflection and refraction beautifully using wave principles. The trouble was, Huygens couldn't easily explain why light cast such sharp shadows. Waves, after all, bend around corners. Think of how sound travels around a doorway, or how water waves wrap around a rock. If light were a wave, shouldn't it do that too? Shouldn't shadows be fuzzy? Newton pointed to those crisp shadow edges as evidence for his corpuscles, and for over a century, that argument basically won. Enter Young, around 1801. And here's what he did. It's so simple, it's almost maddening. He took a beam of sunlight, passed it through a tiny pinhole to create a narrow source, and then let that light fall on a screen with two very thin slits cut side by side, close together. On a wall behind the slits, he observed the pattern that the light made. And if light were made of particles, you'd expect to see two bright bands on the wall, one behind each slit. Simple. Particles go through one slit or the other. They hit the wall. You get two stripes. But that's not what Young saw. Instead, he saw a series of alternating bright and dark bands, a pattern of stripes, many more than two, spread across the wall. And he recognized immediately what this was, because he'd seen the same kind of pattern in water waves. When two sets of waves overlap, they interfere with each other. Where the crest of one wave meets the crest of another, they add up, constructive interference. And you get a bigger wave. Where a crest meets a trough, they cancel out, destructive interference. And you get nothing. The bright bands on Young's wall were places where light waves from the two slits arrived in step, reinforcing each other. The dark bands were places where they arrived out of step, canceling each other out. It was interference. It was unmistakably, undeniably a wave phenomenon. Think about what that means. Light, this thing you see by, this thing that feels so immediate and direct, was revealing itself to be a vibration, an oscillation, a wave rippling through something. And that something was a real puzzle, because waves need a medium. Sound waves travel through air. Water waves travel through water. What was light traveling through? The answer physicists gave was the luminiferous ether, a hypothetical substance that supposedly filled all of space, was perfectly transparent, had no mass you could detect, and yet was rigid enough to support vibrations at incredibly high frequencies. It was a strange idea, honestly, but it seemed necessary if light was a wave, so people accepted it and moved on. Young's double-slit experiment should have settled the wave-particle debate right then and there, but it didn't. Not immediately. In Britain, Newton's corpuscular theory had almost religious status, and Young was attacked viciously. A particularly nasty review in the Edinburgh Review, likely written by Henry Brougham, dismissed Young's work as worthless and essentially tried to destroy his scientific reputation. Young was hurt by it. He actually stepped back from optics for a while and focused on his medical practice and his Egyptology work. But the wave theory didn't need Young alone to carry it. Across the English Channel, a French engineer named Augustin Jean Fresnel independently developed a rigorous mathematical wave theory of light in the 1810s and 1820s that could explain everything: reflection, refraction, diffraction, the bending of light around obstacles, the colors in thin films like soap bubbles. Fresnel's mathematics were powerful and precise, and here's one of the great stories in physics. When Fresnel submitted his wave theory to the French Academy of Sciences in 1818, one of the judges, Siméon Denis Poisson, was actually a supporter of the particle theory. And Poisson found what he thought was a devastating flaw. He worked through Fresnel's equations and showed that they predicted something absurd. If you put a small circular disk in a beam of light, there should be a bright spot right in the center of the shadow, directly behind the disk. "That's ridiculous," Poisson said. "Obviously, there's no bright spot in the middle of a shadow. The wave theory must be wrong." But here's the kicker. Another member of the committee, François Arago, decided to actually do the experiment. And there it was, a bright spot right in the center of the shadow, exactly where Fresnel's wave theory predicted it would be. It's now called the Poisson bright spot, or sometimes the Arago spot, which is a little ironic since Poisson was trying to disprove the theory it confirmed. After that, the wave theory of light was essentially unassailable. By the 1820s and 1830s, the physics community had broadly accepted that light was a wave. So now you've got this beautiful wave theory, and it explains so much. But it raises that nagging question even more urgently. A wave of what? What's actually vibrating? And to answer that, we need to step sideways into a completely different area of physics, one that seemed to have nothing to do with light at all. Electricity and magnetism. People had known about static electricity since the ancient Greeks. Rub amber on fur and it attracts bits of straw. And magnetism was familiar from lodestones, natural magnetic rocks that had been used in compasses for centuries. But for most of history, electricity and magnetism seemed like completely separate phenomena. Unrelated curiosities. That started to change in 1820, when a Danish physicist named Hans Christian Ørsted noticed something remarkable during a lecture demonstration. He had a compass needle sitting near a wire, and when he sent an electric current through the wire, the compass needle moved. It deflected. An electric current was creating a magnetic effect. Electricity and magnetism were connected. This was huge, and it set off a frenzy of experimentation across Europe. Within weeks of hearing about Ørsted's discovery, André-Marie Ampère in France had worked out the mathematical relationship between electric currents and the magnetic forces they produce. Ampère showed that two parallel wires carrying current attract or repel each other depending on whether the currents flow in the same or opposite directions. They behave like magnets, even though there's no magnet anywhere in sight. He essentially founded the science of electrodynamics in a burst of intense work over just a few months in late 1820. But the person who really transformed our understanding of electricity and magnetism and ultimately answered the question of what light is was Michael Faraday. And Faraday's story is one of the most extraordinary in all of science because he came from nowhere. Born in 1791 in South London, the son of a blacksmith, Faraday had almost no formal education. He left school at 13 and was apprenticed to a bookbinder. But he read the books he was binding, especially the science books, and he became obsessed with chemistry and electricity. At 20, he managed to attend a series of lectures by the famous chemist Humphrey Davy at the Royal Institution, took meticulous notes, bound them beautifully, and sent them to Davy asking for a job. Davy hired him as a laboratory assistant, and from that position, Faraday would go on to become arguably the greatest experimental physicist of the 19th century. Faraday couldn't do higher mathematics. He never learned calculus, and in some ways, this was actually an advantage because it forced him to think in pictures, in physical intuitions, in spatial relationships rather than equations. And one of his most profound contributions was the concept of the field. Before Faraday, people thought about electric and magnetic forces the way Newton thought about gravity, as mysterious actions at a distance. One charge pushes another charge, instantly, across empty space, and nobody worries too much about what's happening in the space between them. Faraday didn't buy it. When he sprinkled iron filings around a magnet and saw those beautiful curving lines radiating outward, he didn't see a pretty pattern. He saw something real. He believed those lines of force were actual physical entities, that the space around a magnet or a charged object was filled with a kind of tension, a state of stress, and that this state of the space itself was what transmitted the force. The field wasn't just a mathematical convenience. It was the thing doing the work. This was a radical idea, and many of his contemporaries, the mathematically sophisticated ones especially, dismissed it as the woolly thinking of an uneducated tinkerer. But Faraday kept going. In 1831, he made what might be his most important discovery, electromagnetic induction. He showed that a changing magnetic field creates an electric current. Move a magnet through a coil of wire, and electricity flows. Stop moving the magnet, and the current stops. It's not the presence of the magnetic field that matters. It's the change. That single discovery is the principle behind every electric generator on Earth. Every power plant, whether it burns coal, splits atoms, or catches the wind, is ultimately spinning a magnet inside coils of wire, using Faraday's induction to convert mechanical energy into electrical energy. The lights in your room right now, if they're on, are working because of something Michael Faraday figured out in a basement laboratory in London nearly 200 years ago. But the full implications of what Faraday had uncovered, the fields, the induction, the deep connection between electricity and magnetism, those implications needed someone who could translate Faraday's physical intuitions into the language of mathematics, and that someone was a young Scottish physicist named James Clerk Maxwell, who was about to do something that would put him in the same sentence as Newton and, eventually, Einstein. Maxwell took Faraday's lines of force seriously when almost nobody else in the mathematical establishment did, and starting in the late 1850s, he began constructing a mathematical framework that could describe electric and magnetic fields with precision. He built on the experimental laws, Coulomb's law for electric charges, Ampere's law for currents and magnetic fields, Faraday's law of induction, and he noticed something. The equations, as they stood, had an inconsistency. They didn't quite balance. There was a mathematical gap, and Maxwell had a hunch about where it was hiding. See, Ampere's law worked beautifully for steady currents. Currents that just flow along continuously without changing. But Maxwell realized that when you have a situation where electric charge is building up somewhere, like on the plates of a capacitor that's charging, The current in the wire stops at the plate. It doesn't jump across the gap. And yet, something is happening in that gap. The electric field between the plates is growing. It's changing over time. And Maxwell asked a deceptively simple question. Shouldn't a changing electric field produce a magnetic field, the same way Faraday showed that a changing magnetic field produces an electric current? Think about the symmetry of that for a moment. Faraday had already shown one half of a beautiful reciprocal relationship. Change a magnetic field, and you get an electric effect. Maxwell was proposing the mirror image. Change an electric field, and you get a magnetic effect. He called this missing piece the displacement current, which is a slightly misleading name because it's not really a current in the ordinary sense, not electrons flowing through a wire. It's a changing electric field acting as if it were a current, producing a magnetic field in exactly the way a real current would. And when Maxwell added this term to the equations, everything snapped into balance. The mathematics became self-consistent. The equations closed. Now here's where it gets genuinely breathtaking, and I want you to sit with this because it's one of the most beautiful moments in the entire history of science. Once Maxwell had all four equations written down, what we now call Maxwell's equations, he started playing with them mathematically, combining them, rearranging them, doing the kind of algebraic manipulation that physicists do when they want to see what their equations are really telling them. And what fell out was a wave equation. The equations predicted that electric and magnetic fields could sustain each other, leapfrogging through space, a changing electric field creating a magnetic field, that changing magnetic field creating an electric field, on, propagating outward as a self-sustaining wave. And when Maxwell calculated the speed of this wave from the known constants of electricity and magnetism, the permittivity and permeability of free space, numbers that had been measured in laboratories having nothing to do with optics, the speed came out to almost exactly 300,000 kilometers per second. The speed of light. Maxwell wrote, in what might be the most understated bombshell in physics, that the agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. That's it. That's the moment. Light. This thing that humans had wondered about since the very beginning of wondering turned out to be ripples in electric and magnetic fields, the same fields that make a compass needle swing and make a balloon stick to your hair after you rub it, the light from a candle, the warmth of the sun on your face, the colors of a sunset, all electromagnetic waves, differing only in their wavelength and frequency. And the thing is, Maxwell's equations didn't just explain visible light. They predicted that electromagnetic waves could exist at any frequency. There was nothing special about the narrow band our eyes happened to detect. There should be waves with longer wavelengths than red light and waves with shorter wavelengths than violet, stretching out in both directions essentially without limit. Maxwell published this work in stages through the 1860s, culminating in his great 1873 treatise on electricity and magnetism. And then, tragically, he died in 1879 at the age of just 48 from abdominal cancer, the same disease that had killed his mother at the same age. He never saw experimental confirmation of his prediction. That confirmation came from Heinrich Hertz, a German physicist working in Karlsruhe in the late 1880s. Hertz built an apparatus, really quite simple in concept, with a spark gap transmitter on one side of his laboratory and a receiver loop with its own tiny gap on the other. When he triggered sparks in the transmitter, he could detect tiny sparks jumping across the gap in the receiver, across the room, with no wire connecting them. He was generating and detecting electromagnetic waves, radio waves specifically. Hertz measured their speed and found it matched the speed of light. He showed they could be reflected, refracted, and polarized, just like light. Maxwell had been right about everything. There's a poignant detail here. When someone asked Hertz what use these electromagnetic waves might have, he reportedly said something to the effect of, "It's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right." Within 2 decades, Guglielmo Marconi was sending radio signals across the Atlantic, and the entire age of wireless communication, radio, television, radar, Wi-Fi, the cell phone you probably have on your nightstand right now, all of it flows directly from Maxwell's equations and Hertz's confirmation. Every time you connect to a wireless network, you're surfing on electromagnetic waves that Maxwell predicted from pure mathematics before anyone had ever detected one. But here's the thing that was quietly lurking inside Maxwell's triumph, something that wouldn't fully detonate for another couple of decades. Maxwell's equations gave a specific speed for electromagnetic waves, the speed of light, about 299,792 kilometers per second. But speed relative to what? In Newtonian mechanics, speeds are always relative to something. You say a car is going 60 miles an hour, and you mean relative to the road. A ball thrown on a moving train has one speed relative to the train, and a different speed relative to the ground. So when Maxwell's equations spit out this speed for light, physicists naturally assumed it must be the speed relative to some medium, the luminiferous ether that had been hypothesized as the substance through which light waves propagate, the way sound waves propagate through air. This made sense on the surface. Every other wave anyone had ever encountered needed a medium. Sound needs air or water or some material to travel through. Ocean waves need water. So light waves, it seemed obvious, must need ether. And if the ether existed, then the Earth must be moving through it as it orbits the sun, which means there should be an ether wind. And you should be able to detect it by measuring tiny differences in the speed of light in different directions. If you're moving through the ether, light going into the headwind should appear slightly slower, and light going with the wind should appear slightly faster, just like sound is affected by wind. In 1887, Albert Michelson and Edward Morley, working in Cleveland, Ohio, built an extraordinarily precise instrument called an interferometer to detect exactly this effect. Their device split a beam of light into 2 perpendicular paths, sent them out and back along those paths, and then recombined them. If one beam traveled slightly faster than the other, because of the Earth's motion through the ether, the recombined beams would be slightly out of step. They'd show an interference pattern shift. Michelson had already tried a version of this experiment in 1881 in Potsdam, but the Michelson-Morley experiment of 1887 was far more sensitive, capable of detecting an ether wind far smaller than what Earth's orbital speed should produce. They found nothing, no shift, no ether wind. The speed of light was the same in every direction, no matter how they oriented their apparatus, no matter what time of year they measured. It was one of the most famous null results in the history of science, and it was deeply, deeply troubling. If there was no detectable ether wind, then either the Earth happened to be perfectly stationary with respect to the ether, which was absurd since the Earth is orbiting the Sun at 30 kilometers per second, or something was fundamentally wrong with the whole picture. Various physicists tried to patch things up. The Irish physicist George Fitzgerald and the Dutch physicist Hendrik Lorentz independently proposed that objects moving through the ether physically contract in the direction of motion by exactly the right amount to cancel out the expected effect. It was a clever mathematical fix, and the Lorentz transformations that came out of it were correct equations. They're still used today. But the physical explanation, that matter literally squishes because of its interaction with the ether, felt ad hoc. It felt like a Band-Aid. The ether was becoming one of those ideas that required more and more elaborate rescuing, more and more special pleading to keep alive. And meanwhile, something else was going wrong. This time, not with light, but with heat. By the end of the 19th century, physicists had a very successful theory of thermal radiation, the light and heat emitted by hot objects. You know how a piece of metal, when you heat it up, first glows dull red, then orange, then yellow, then white? Physicists were trying to calculate the exact spectrum of that radiation, the precise distribution of energy across all the different wavelengths. And they had a formula based on classical physics that worked beautifully for long wavelengths. But when they extended it to short wavelengths, ultraviolet and beyond, the formula predicted that the energy should increase without limit. A hot object should radiate infinite energy at short wavelengths. This was obviously absurd. It was so obviously wrong that it got a dramatic name: the ultraviolet catastrophe. In December of 1900, a German physicist named Max Planck found a mathematical trick that fixed the problem. He assumed that energy couldn't be emitted or absorbed continuously, in any arbitrary amount, but only in discrete little packets, quanta, whose energy was proportional to the frequency of the radiation. He introduced a new constant, an incredibly tiny number now called Planck's constant, and with this one assumption, his formula matched the experimental data perfectly across all wavelengths. Planck himself wasn't entirely comfortable with what he'd done. He saw it more as a mathematical device, a calculational trick that happened to work. He spent years trying to find a way to derive the same result without the quantum assumption. He couldn't, but someone else took the quantum idea and ran with it. In 1905, a 26-year-old patent clerk in Bern, Switzerland, you already know his name, published a paper arguing that light itself actually comes in these discrete packets of energy. Not just that emission and absorption happen in chunks, but that light itself is quantized. Albert Einstein called these packets light quanta, and he used the idea to explain the photoelectric effect, a puzzling phenomenon where light shining on a metal surface ejects electrons, but only if the light's frequency is high enough. Brighter light of too low a frequency does nothing, no matter how intense. Classical wave theory couldn't explain this at all. But if light comes in individual packets, each carrying an energy proportional to its frequency, then it makes perfect sense. Each packet either has enough energy to knock an electron free, or it doesn't. Brightness just means more packets, but if each individual one is too weak, none of them can do the job. This was radical. Remember, by 1905, the wave theory of light had been triumphantly confirmed for nearly a century. Young's double-slit experiment, Fresnel's diffraction theory, Maxwell's electromagnetic waves, Hertz's radio waves. Light was a wave. That was settled. And now Einstein was saying, actually, it also behaves like a particle, not instead of being a wave, but in addition to being a wave. Light is somehow both. And that same year, 1905, Einstein's miracle year, he published 3 other groundbreaking papers. One on Brownian motion, providing powerful evidence that atoms are real, which would have vindicated Boltzmann had he lived to see it. One on special relativity, and one deriving the most famous equation in all of physics. Special relativity came directly from the tension Maxwell's equations had created, Einstein didn't start from the Michelson-Morley experiment, actually. There's some debate about how much he even knew about it. What he started from was a thought experiment he'd been mulling over since he was 16 years old. What would it be like to ride alongside a beam of light? If you could travel at the speed of light next to a light wave, the wave would appear frozen, a static ripple of electric and magnetic fields hanging motionless in space. But Maxwell's equations don't allow that. There's no solution to Maxwell's equations that looks like a stationary electromagnetic wave. The equations demand that electromagnetic waves move at the speed of light, always, period. So Einstein took this seriously. He proposed two postulates. First, the laws of physics are the same in all inertial reference frames. No experiment can tell you whether you're truly moving or truly stationary. And second, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. That second postulate sounds almost innocent, but when you follow its logic, it demolishes the Newtonian framework of absolute space and absolute time that had stood for over 2 centuries. If the speed of light is the same for everyone, then something else has to give. And what gives is your assumptions about time itself. That's what gives. Time, it turns out, is not universal. It doesn't tick at the same rate for everyone. 2 people moving relative to each other will disagree about how much time has passed between 2 events, and here's the really unsettling part. They're both right. There's no real answer. There's no cosmic clock sitting outside the universe keeping the one true time. Time is local. Time is personal. Time depends on how you're moving. Let that settle for a moment, because it's genuinely one of the strangest things physics has ever told us, and yet it's not a guess, not a philosophical opinion. It's a logical consequence of the speed of light being constant, and it's been confirmed by experiment over and over and over again. Here's how it works, intuitively. Imagine you're standing on a train platform, and a train is moving past you at some significant fraction of the speed of light. Let's say 60% of light speed, which is absurdly fast, but we need these extreme speeds for the effects to be noticeable. On that train, someone has set up a simple clock. It's the simplest clock you can imagine. A photon of light bouncing vertically between 2 mirrors, one on the floor and one on the ceiling. Every time the photon completes a round trip, floor to ceiling and back, that's 1 tick of the clock. Simple, right? From the perspective of the person on the train, the light just goes straight up and straight down. The distance is fixed, the speed of light is fixed, so the tick rate is fixed. Nothing unusual. But now think about what you see from the platform. The train is moving sideways, so from your perspective, that photon isn't going straight up and down. It's tracing a diagonal path, up and to the right, then down and to the right, because the train has moved forward during the time the photon was traveling. The photon has to cover a longer diagonal distance. But, and here's Einstein's second postulate doing its work, the speed of light is the same for you as it is for the person on the train. Same speed, longer path. That means more time elapses between ticks from your perspective. The moving clock runs slow, not because it's broken, not because of some mechanical effect. The geometry of space-time itself makes it so. This is time dilation, and the formula Einstein derived is elegant. The time experienced by the moving observer is the stationary time multiplied by the square root of 1 minus v squared over c squared, where v is the relative velocity and c is the speed of light. At everyday speeds, driving a car, flying a plane, V is so tiny compared to c that this factor is essentially 1. The effect is there, but it's billionths of a second over an entire lifetime. You'd never notice. But as V approaches c, the factor shrinks dramatically. At 90% the speed of light, a moving clock runs at about 44% the rate of a stationary one. At 99%, it's down to about 14%. Time genuinely slows down. And length does something similar. An object moving relative to you appears contracted along its direction of motion. This is length contraction, the same idea Fitzgerald and Lorentz had proposed to explain the Michelson-Morley result. But now it's not an ad hoc patch. It falls out naturally from the postulates. It's not that the object is being squeezed by some force. Space itself is different for observers in relative motion. And then there's the relativity of simultaneity, which might be the most philosophically jarring consequence of all. Two events that are simultaneous for one observer are not necessarily simultaneous for another observer moving relative to the first. Think about what that means. If I say 2 lightning bolts struck at the exact same moment, one at the front of a moving train and one at the back, a person standing on the platform might agree they were simultaneous. But a person sitting in the middle of the train, moving toward one strike and away from the other, will see the light from the front strike arrive first. And since the speed of light is the same in all directions for all observers, that person will conclude the front strike happened first. Not appeared to happen first. Actually happened first, in their reference frame. Simultaneity is not absolute. The ordering of events can depend on your state of motion. That's wild. That's genuinely wild. Now, Einstein published all of this in June of 1905, and a few months later, almost as an afterthought, he published a short follow-up paper, just 3 pages, where he worked out an additional consequence. If a body emits energy in the form of radiation, its mass decreases. The energy carried away by the radiation corresponds to a specific amount of mass, and the relationship between them is E equals mc squared. Energy equals mass times the speed of light squared. The speed of light squared is an enormous number, about 9 times 10 to the 16th in metric units, which means a tiny amount of mass corresponds to a staggering amount of energy. A single gram of matter, fully converted to energy, would release roughly the same energy as 20,000 tons of TNT. That's not a bomb designer's fantasy. That's just what the equation says. And it's true. It's the principle behind nuclear reactions, behind the energy output of stars, behind the reason the sun has been burning for 4.5 billion years without running out of fuel. The sun is converting mass to energy, about 4 million tons of mass every second, and it barely notices. So by the end of 1905, Einstein, a 26-year-old patent clerk in Bern, Switzerland, who couldn't get a university teaching position, had fundamentally rewritten the foundations of physics. He'd shown that light has particle-like properties, provided strong evidence for the atomic theory, demolished absolute space and time, and derived the most famous equation in science. It's hard to overstate how extraordinary that is. But he wasn't done. He knew special relativity had a limitation. It only applied to inertial frames, to observers moving at constant velocities relative to each other. It said nothing about acceleration, and it said nothing about gravity. That bothered him. And in 1907, sitting in his chair at the patent office, he had what he later called the happiest thought of his life. He imagined a person falling freely, falling off a roof, say. During the fall, that person would feel weightless. They wouldn't feel gravity at all. A ball they released from their hand would float beside them, falling at the same rate. Inside that little falling reference frame, it would be as if gravity didn't exist. And Einstein realized this meant something profound. Gravity and acceleration are locally indistinguishable. If you're in a closed box and you feel a force pulling you toward the floor, you cannot tell, by any experiment done inside the box, whether you're sitting on the surface of a planet or being accelerated upward by a rocket at the same rate. This is the equivalence principle, and it became the cornerstone of general relativity. But getting from that insight to a complete theory took Einstein nearly a decade. The mathematics he needed didn't exist in his toolbox. He had to learn differential geometry, tensor calculus, the mathematics of curved spaces that had been developed by Bernhard Riemann and others in the 19th century. He struggled. He made wrong turns. He published preliminary versions that had errors. He collaborated with his friend Marcel Grossmann, a mathematician who helped him navigate the formalism. There were periods of intense frustration, periods where he thought he'd found the answer only to discover inconsistencies. And meanwhile, he had competition. David Hilbert, one of the greatest mathematicians alive, became interested in the problem in 1915 and began working toward the same goal. There's a famous near-simultaneous arrival. Einstein presented his final correct field equations to the Prussian Academy of Sciences on November 25, 1915, and Hilbert submitted a paper with essentially equivalent results just 5 days earlier, on November 20th. The priority question has been debated by historians for a century, though most give Einstein the primary credit because the physical insights were his, and Hilbert's published version actually went through revisions that may have incorporated Einstein's results. Regardless, the theory that emerged is one of the most beautiful constructions in all of human thought. Here's the core idea. Forget the Newtonian picture of gravity as a force pulling masses toward each other across empty space, that mysterious action at a distance that Newton himself was uncomfortable with. In general relativity, gravity isn't a force at all. It's geometry. Mass and energy curve the fabric of space-time, and objects move along the straightest possible paths through that curved space-time. Those paths are called geodesics. The Earth doesn't orbit the Sun because an invisible force is pulling it inward. The Earth is moving in a straight line through curved space-time, space-time that's been warped by the Sun's enormous mass. It's following the most natural path available to it, and that path happens to be an ellipse when viewed in our three-dimensional spatial perspective. Think of it this way. Imagine a bowling ball sitting on a stretched rubber sheet. The ball creates a dip, a curve in the sheet. Now roll a marble nearby. The marble doesn't go in a straight line. It curves toward the bowling ball, spirals around it, maybe falls in. Not because the bowling ball is reaching out and grabbing it, but because the surface it's rolling on is curved. That's a rough analogy. Imperfect because space-time curvature is four-dimensional and involves time as well as space. But it captures the essential flavor. Einstein's field equations describe exactly how mass and energy determine the curvature of space-time and how that curvature determines the motion of mass and energy. They're written compactly. The Einstein tensor equals 8 pi g over c to the fourth times the stress energy tensor. But packed inside that compact notation is an extraordinary amount of structure. 10 coupled nonlinear partial differential equations. They're notoriously difficult to solve. Exact solutions exist only for highly symmetric situations. But the predictions they make are stunning. The first triumph came almost immediately. Mercury's orbit had a known anomaly. It's perihelion, the point of closest approach to the Sun, precessed slightly more than Newtonian gravity predicted. The discrepancy was tiny, about 43 arcseconds per century, but it had nagged astronomers for decades. Leverrier, the same astronomer who had predicted Neptune's existence from similar orbital anomalies, had even proposed a hidden planet called Vulcan, lurking near the Sun, to explain it. No such planet existed. When Einstein calculated Mercury's orbital precession using his new field equations, he got the exact right answer. 43 arcseconds per century, falling out of the mathematics with no adjustable parameters. He later said his heart shuddered in his chest when he saw the result. The second prediction was even more dramatic, and it's the one that made Einstein a global celebrity. General relativity predicted that light itself should be bent by gravity, that a beam of light passing near a massive object would follow the curved spacetime and deflect. Newton's gravity actually predicts a slight deflection too, if you treat light as particles with some effective mass, but Einstein's theory predicted exactly twice the Newtonian value. The way to test this was to observe stars near the edge of the Sun during a total solar eclipse. The Sun's glare would be blocked, and you could see whether the apparent positions of stars near the Sun's limb were shifted compared to their normal positions. In 1919, the British astronomer Arthur Eddington organized 2 expeditions, one to Sobral in Brazil, one to the island of Principe off the west coast of Africa, to photograph the eclipse of May 29th. The results, announced in November 1919, confirmed Einstein's prediction. The headlines were extraordinary. The Times of London declared, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Einstein went from being known mainly within physics to being the most famous scientist on Earth, practically overnight. But general relativity predicted things even Einstein wasn't comfortable with. Karl Schwarzschild, a German physicist serving on the Eastern Front in World War I, found an exact solution to Einstein's field equations for the spacetime around a spherical, non-rotating mass. The solution had a peculiar feature. At a certain radius, now called the Schwarzschild radius, the mathematics seemed to break down. For an object like the Sun, this radius was deep inside the star, so it didn't matter physically. But what if a star were compressed below its Schwarzschild radius? The solution implied that nothing, not even light, could escape from within that boundary. The object would be invisible, a point of no return hanging in the fabric of space-time itself. Schwarzschild sent his solution to Einstein in early 1916 from the trenches. Think about that for a moment. Here's a man surrounded by artillery fire, suffering from a painful autoimmune disease, pemphigus, that would kill him within months, and he's sitting there solving the most complicated set of equations in the history of physics. Einstein was genuinely surprised that an exact solution even existed. He'd been working with approximations, assuming the full equations were too difficult to solve analytically. And here was Schwarzschild, dying on the Eastern Front, handing him an exact answer on a plate. Schwarzschild passed away in May 1916 at the age of 42. He never saw what his solution would come to mean. For decades, most physicists, including Einstein, believed the Schwarzschild radius was a mathematical curiosity, not something that could actually exist in nature. The idea that a real physical object could collapse to that degree seemed absurd. In the 1930s, Subrahmanyan Chandrasekhar, a young Indian physicist barely out of his teens, calculated that a white dwarf star above a certain mass, about 1.4 times the mass of our Sun, couldn't support itself against gravitational collapse. Arthur Eddington, the same Eddington who'd confirmed general relativity, publicly ridiculed Chandrasekhar at a Royal Astronomical Society meeting, essentially saying, nature would surely find a way to prevent such a thing. It was a humiliating moment. Chandrasekhar was right, of course, and Eddington was wrong, but it took decades for the physics community to fully come around. In 1939, Robert Oppenheimer, yes, the same Oppenheimer who would later lead the Manhattan Project, co-authored a paper with Hartland Snyder showing that a sufficiently massive star, once it exhausted its nuclear fuel, would indeed collapse past the Schwarzschild radius. The term black hole wouldn't be coined until 1967, when the physicist John Archibald Wheeler used it at a conference, but the concept was there. Space-time could curve so drastically that it pinched off a region from the rest of the universe. And here's what's really wild about this. General relativity doesn't just predict black holes as exotic objects out in deep space. It predicts that the entire universe itself has a large-scale geometry. Einstein realized this almost immediately after publishing his field equations. In 1917, he applied general relativity to the cosmos as a whole, and he found something disturbing. His equations naturally predicted a universe that was either expanding or contracting. It wouldn't just sit still. But Einstein, like almost everyone in 1917, believed the universe was static and eternal. So he added a term to his equations, the cosmological constant, usually written as the Greek letter lambda, specifically to hold the universe still, to balance gravity and keep everything from collapsing inward. He later called it his greatest blunder, because in 1929, Edwin Hubble, working at the Mount Wilson Observatory in California with its 100-inch telescope, the largest in the world at the time, demonstrated that distant galaxies were receding from us, and the farther away they were, the faster they were moving. The universe was expanding. The Belgian physicist Georges Lemaitre had actually predicted this a couple of years earlier, working directly from Einstein's field equations without the cosmological constant, and he'd proposed that if you ran the expansion backward in time, everything would converge to what he called the primeval atom, a single point of unimaginable density. This was the first version of what we now call the Big Bang theory, and it came straight out of general relativity. So here's the picture by the late 1920s. General relativity is telling us about the large-scale structure and history of the entire cosmos. But meanwhile, something equally revolutionary has been happening at the smallest scales. And this is where we need to circle back to that thread we left hanging earlier, the quantum. Remember Planck's desperate move in 1900, introducing the idea that energy comes in discrete packets, and Einstein's 1905 paper arguing that light itself is quantized into particles? Photons? Those ideas were radical, but they were just the opening act. The real quantum revolution, the one that would shake physics to its philosophical foundations, unfolded in the 1920s, and it happened with breathtaking speed. In 1913, Niels Bohr, a young Danish physicist working in Manchester with Ernest Rutherford, proposed a model of the atom that was frankly bizarre. Rutherford had recently discovered that atoms have a tiny, dense nucleus surrounded by orbiting electrons. The problem was that classical electromagnetism said those orbiting electrons should continuously radiate energy and spiral into the nucleus. Every atom should collapse in a fraction of a second. Obviously, atoms don't do that. Bohr's solution was to simply declare, by fiat almost, that electrons could only occupy certain specific orbits, quantized orbits, and that they didn't radiate energy while in those orbits. They could jump between orbits, emitting or absorbing a photon of exactly the right energy, but they couldn't exist in between. It was a strange hybrid, classical orbits with quantum rules bolted on, and Bohr himself knew it wasn't a complete theory. But it worked remarkably well for hydrogen, predicting the wavelengths of hydrogen's spectral lines with stunning accuracy. For about a decade, physics was in an awkward adolescence. The old classical framework was clearly broken at the atomic scale, but nobody had a coherent replacement. There were quantum rules grafted onto classical mechanics, and they worked for simple cases, but the whole thing felt like a patchwork. Then, in 1925 and 1926, two entirely different mathematical frameworks emerged almost simultaneously, and they turned out to be saying the same thing in different languages. Werner Heisenberg, a 23-year-old German physicist, was the first. In June 1925, recovering from hay fever on the island of Helgoland in the North Sea, he developed a formulation of quantum mechanics based on matrices, arrays of numbers that don't commute, meaning A times B doesn't equal B times A. This was deeply strange. In ordinary arithmetic, 3 times 5 is the same as 5 times 3. But Heisenberg was saying that at the quantum level, the order of operations matters in a fundamental way. The physical quantities you measure, position, momentum, are represented by these non-commuting matrices, and the fact that they don't commute is directly connected to the uncertainty principle he would articulate 2 years later. You cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you pin down one, the more the other eludes you. This isn't a limitation of your instruments. It's built into the fabric of reality. Then, in early 1926, the Austrian physicist Erwin Schrödinger, working in Zurich, developed a completely different approach. His version was based on wave equations, smooth, continuous, familiar-looking mathematics. Schrödinger's equation describes how a wave function evolves over time, and the wave function encodes the probability of finding a particle in a given state. If Heisenberg's approach felt alien and abstract, Schrödinger's felt almost classical, almost comforting. Physicists gravitated toward it because they could visualize waves. But here's the thing. Paul Dirac and others soon proved that the two formulations were mathematically equivalent. They were the same theory wearing different clothes. Matrix mechanics and wave mechanics were just two ways of describing the same underlying quantum reality. And what a strange reality it was. The wave function doesn't tell you where a particle is. It tells you the probability of finding it in various places if you look. Before you measure, the particle doesn't have a definite position in any classical sense. It exists in a superposition of possibilities. When you make a measurement, the wave function collapses. The probabilities resolve into a single outcome. This bothered a lot of people. It still bothers a lot of people. Einstein famously refused to accept it, spending the rest of his life arguing that quantum mechanics must be incomplete, that there must be hidden variables underneath, that God does not play dice. Bohr pushed back, insisting that the probabilistic description was fundamental, not a sign of ignorance, but a feature of nature itself. Their debates, particularly at the Solvay conferences of 1927 and 1930, are some of the most extraordinary intellectual exchanges in the history of science. Einstein would propose ingenious thought experiments designed to show that quantum mechanics led to contradictions, and Bohr would stay up all night finding the flaw in Einstein's argument. Every time, Bohr won. But Einstein never conceded. In 1928, Dirac did something remarkable. He combined quantum mechanics with special relativity. Remember, Schrödinger's equation wasn't relativistic. It didn't account for particles moving near the speed of light, and produced the Dirac equation. This single equation described the electron in a way that was consistent with both quantum mechanics and special relativity, and it naturally predicted the electron's spin, a property that had been observed but never explained from first principles. But the equation also predicted something no one expected. For every particle, there should exist an antiparticle, identical in mass, but opposite in charge. Dirac initially wasn't sure what to make of this. Some people thought the antiparticle of the electron might be the proton, but the masses were wrong. Then, in 1932, Carl Anderson at Caltech found it, the positron, in cosmic ray tracks in a cloud chamber. Antimatter was real. A purely mathematical prediction from combining two theories had conjured a new form of matter into existence. That's the power of what physics had become. By the mid-20th century, these two pillars, general relativity governing the very large, quantum mechanics governing the very small, were both spectacularly successful in their own domains. General relativity predicted the expansion of the universe, black holes, gravitational lensing, gravitational time dilation. Your GPS satellites have to correct for it, by the way, or your position would drift by kilometers per day. Quantum mechanics gave us semiconductors, lasers, nuclear energy, MRI machines, the entire framework of modern chemistry. The phone in your pocket, if you have one on your nightstand right now, runs on quantum mechanics. Every transistor in its processor is a quantum device. The screen, if it's an LED screen, emits light through quantum processes. You are surrounded by quantum technology. But here's the deep puzzle, the one that haunted the second half of the 20th century and still haunts physics today. These two theories don't fit together. General relativity is a theory of smooth, continuous space-time, a fabric that bends and curves. Quantum mechanics is a theory of discrete jumps, probabilities, and uncertainty. When you try to apply quantum mechanics to gravity itself, when you try to write down a quantum theory of the gravitational field, the mathematics produces infinities. Not manageable infinities that you can tame with clever techniques, the way physicists learned to handle infinities in quantum electrodynamics in the 1940s through the work of Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. No, the infinities in quantum gravity are untamable. The theory is, in the technical language, non-renormalizable. It breaks. This is the great unfinished business of physics. String theory, loop quantum gravity, and other approaches have been proposed, each with passionate advocates, each with serious, unresolved problems. String theory, which emerged in the 1970s and 1980s, suggests that the fundamental constituents of nature aren't point particles, but tiny vibrating strings, and that their different vibrational modes correspond to different particles. It naturally includes gravity, but it requires extra spatial dimensions, 6 or 7 of them, curled up so small we can't detect them. And it comes in a vast landscape of possible solutions, making it extraordinarily difficult to test. Loop quantum gravity takes a different approach, trying to quantize space-time itself, suggesting that space at the smallest scales isn't smooth, but has a discrete, granular structure, like a fabric woven from tiny loops. Neither approach has produced a confirmed experimental prediction that distinguishes it from the standard framework. And so physics, as you drift off tonight, is in a fascinating place. We've come so far from those first Greek philosophers staring at the night sky, wondering what the stars were made of. From Aristotle's crystal spheres, to Newton's universal gravitation, to Einstein's curved space-time. From the caloric theory of heat, to Boltzmann's dancing atoms, to Planck's desperate quantum. From Faraday's invisible field lines to Maxwell's equations to the photon, each generation thought they were close to the final answer, and each generation discovered that nature had another layer, another surprise, another depth they hadn't imagined. What's beautiful about this whole story, and I hope you felt this as we've wandered through it together, is that physics isn't a collection of facts. It's a conversation between human beings and the universe, carried on across centuries, across cultures, across wars and plagues and revolutions. Each person we've talked about tonight, Galileo dropping his thought experiments from imaginary towers, Newton alone in Woolsthorpe during the plague, Faraday in his basement laboratory with his coils of wire, Boltzmann fighting for atoms no one believed in, Einstein riding his imaginary beam of light, Schwarzschild solving equations in the trenches, Chandrasekhar enduring public humiliation for being right. Each of them picked up a thread left by someone before them and followed it a little further into the dark. They didn't always know where it led. They were often wrong. They argued, they doubted, they sometimes despaired. But they kept asking, they kept looking, and the universe, in its own quiet way, kept answering. The questions that remain: what is dark matter? What is dark energy? How do you reconcile gravity with the quantum world? What happened in the first fraction of a second after the Big Bang? Is there a multiverse? What is time, really? These are not signs of failure. They're invitations. They're the next part of the conversation, waiting for someone to pick up the thread. Maybe someone is working on it right now in a small office somewhere, or scribbling on a napkin, or lying awake in bed turning an idea over and over, the way you might turn over a smooth stone in your hand, feeling its weight, its shape, sensing that there's something there, something just out of reach, something that will make sense in the morning, and that's enough for tonight. The story goes on. It always goes on. But you can rest now and let the universe keep its secrets for a little while longer, turning slowly in the dark, patient and vast and full of things still waiting to be understood.